Hello, let's talk about boundary conditions. In finite element modeling, the mesh defines the structure and organization and geometry of our model, whereas the boundary conditions define what we do to it. That's the loads and the constraints that we apply to mimic real life situations. And in FEBio, there are a number of things that kind of fall under this general category of boundary conditions. So if we look in our FEB file, here on the left, we have boundary conditions, but we also have loads and constraints. And then we also have initial conditions, which sounds like boundary conditions, contact, which is could be called a boundary condition, and then rigid also contains some things that can be considered boundary conditions. And so let's, in this video, go over kind of what all those are kind of used for, just an overview of that. And then I'll give an example that we use in my lab where we switch from a torque load to an applied rotation. Let's get started. First off, boundary conditions. When we right click here, we have three options: nodal, surface, and linear constraints. Generally, this boundary conditions option is for taking a node or a surface and applying some sort of constrained motion to it. So if I click on add nodal boundary condition, then these are all things we can do to individual or groups of nodes. So we can say zero displacement. This node or group of nodes don't get to move. And we can define which axes that applies in, or zero rotation. We can make them rigid and say, okay, these ones, even though it's within this larger deformable mesh, these nodes don't get to move relative to each other. And prescribed rotation, displacement, deformation, etc. All things we can apply to nodes or surfaces. Now, if we come to loads, this is not constraining the motion. This is applying a load and seeing how the motion happens. So in boundary conditions, we apply a motion and see how the forces happen. Loads, we apply a force and see how the displacements happen. So if we right click here, again, nodal, surface, or body. So nodal, we can have a load, force, basically how hard are you going to push? And this will apply it to the nodes that you select. If we do surface load, then we have more options, pressure, traction, again, a force, and so you can apply what you need. In our model, we have 8 boundary conditions and 2 loads. And so let's talk about what those are. This rigid definition takes the C0 bone, which is this yellow one on top, and it takes the TM or tectorial membrane, and it makes them rigidly attached. So basically we said that's where it's going to happen. And if I scroll down, then it's going to take the nodes that were selected. So right here at the top of the tectorial membrane, and it's going to rigidly attach them to, forced, which is the name of the rigid body that is C0. And then the same thing happens with the transverse ligament, a small collection of nodes. This is underneath the tectorial membrane in pink, and it's rigidly attached. And then this is actually really interesting. This model was previously used to calculate the deformation of the bones themselves. Right now, all the bones are modeled as rigid bodies, so there's no deformation within the bones. But previously, when they were looking at deformation in the bones, they still wanted to be able to get some like really high quality angles and displacement values and things like that as the bone and like all together. So what they did as kind of a workaround is they said, okay, we're going to select four nodes that make up one tetrahedral element, and we're going to define those to be a rigid body. That's what these four nodes highlighted here are. So then that way they could say, okay, we named this new little rigid body C1. In the post-processing, we can go and we can look at the rigid Euler angle of that rigid body and use that as a proxy for the whole body Euler angle. Now that the entire bone is its own rigid body, this is kind of vestigial and isn't needed anymore, but very interesting. Our pressure loads, we have two pressure loads. One is a positive and one is a negative. So we have a positive pressure that sandwiches down the intervertebral discs between our bones, and then one that takes that same pressure and applies it outward to the inner surface of that. So this kind of defines our pre-strain conditions in our model so that the model behaves appropriately. This brings us to initial conditions. We can add initial condition if we right click, and we'll see that pre-strain is actually an option in our initial conditions. And whether this is the right option for you, I can't tell. What I do know is that in our models, we use this pressure load as our pre-strain, and we don't use pre-strain. I've also seen plenty of models where in order to apply a pre-strain, they take one step in the analysis to take an undeformed ligament and then they stretch it and place it and attach it to the bone that it should be attached to in that initial step. And then from there, it all runs together and the ligament is rigidly attached to the bone after that point. So I've seen that with like MCL, LCL, ACL, PCL kind of things, and maybe applicable to your model depending on what you're working with. But maybe the pre-strain would work too. It's there, or maybe you need to apply some of these. I've never really seen them before, so I don't know. So that's initial conditions. Contact can be a beast, but we love contact. It's very important to define where two different parts interact and how they interact. And if you want to learn more about contact, that's a video of its own, at least, probably multiple. Constraints, I've also never really seen this, but this seems to be for kind of niche uses. So you could define a symmetry plane or a rigid wall. This edge to surface sliding contact or contact potential seems like some more advanced boundary conditions. If you need those, I would talk to the FEBio development team. And last but not least, we have rigid. This is where we apply most of our loads that actually feel like loads in our models. So if we open this up, we have rigid fixed. So we take a rigid body and we fix it in all 6 degrees of freedom. And then we also have this rigid moment applied. So this is a load applied to the forced rigid material, which is this top one, and it goes about the x-axis. So U, V, W are just x-axis, y-axis, z-axis, and the value is negative 1500. Our units are newtons, millimeters, so negative 1500 Newton millimeters, or 1.5 Newton meters. And so that applies a torque in extension, and we can see that in this xplot file. Basically, it applies this load and the model extends. Something else I wanted to talk about, though, is the load controllers of these models. Our pressure load, both of them, pressure loads, are applied in the initial time step, and then our rigid load, this rigid moment, is applied after. So if we open up the curve editor, then we can see that. So if we come to loads, and then any of these pressure loads, we can see that from 0 to 1 in time, it ramps up from 0 to 1. So that pressure load gradually reaches its full potential and then stays constant after that. However, the rigid force starts at 0 and then begins to ramp up at time equals 1 up to time equals 2. So we have a 2-second simulation. And so first the pressure and then second the load. That's that. That's kind of an overview of the boundary conditions. If you have more questions, the FEBio manual is a great place to start. With that, let's get into changing this model. So this is a torque applied model. It has a moment. This is good for collecting the angle of the model. I've actually gone through and I've done this here's my little spreadsheet. So in flexion and extension and right and left axial rotation, I've collected the Euler angle of the occiput, the very top bone. In the unfused configuration, in the 5-6 fused configuration, and the 5-7 fused configuration. This is the 5-7 fused configuration. We can see these 3 bones are all the same color, so they're all part of one rigid body. Now, what I want to do is I want to take this angle that was reached in flexion and extension and right and left axial rotation. I want to apply that now so that we can look at the forces and stresses. Torque is good for angle and like the displacement of the model, but I want to apply now the motion in order to get a look at the stresses and forces that the model experiences. And so this is the angle in radians, by the way. I'm going to take this value and just remember it. That's why I wrote it down. And we're going to apply it to this model. So I'm going to take this flexion angle and just keep it right here. Let's switch. So rigid moment, we can delete that. Hitting delete on my keyboard, it's gone. And now we're going to come into rigid, add a rigid constraint, and make it a rigid rotation. Okay, rigid material, I'm going to apply, this one is called forced. So I want to apply it to this occiput, which its rigid body is called forced. And I want this to be about the x-axis, because I'm going to do flexion. And so that would be RU, rigid rotation. And using the right hand rule, that would be a positive rotation. And so here is my value. So in radians, 0.67, what was that? 62. 0.6762. Amazing. And now we're ready to go, right? Not quite. Because this is a rotation in one plane, but that actually leaves it open to all sorts of out-of-plane motion. And so since that isn't prescribed, it doesn't know what to do. It works with the load, but not with the applied rotation. So we actually have to fix its motion in that plane. So I'm going to add one more rigid constraint. I'm going to say rigid fixed. And I'm going to say, okay, again, forced. And I want this not to move. Well, we want it to displace, but we don't want it to rotate. So X rotation, that's the one we're doing. But Y rotation, gone. Z rotation, gone. And now it should work okay. So at this point, I'm ready to hit run and we'll be good to go. Now, how do we make it an extension model? All we have to do is look here and say, okay, extension 0.7195. All I have to do is come to this rigid rotation and make it negative this time, 0.7195. Is that right? So that's right. So the negative makes it extension. What about axial rotation? Well, pretty straightforward, mostly. First, of course, okay, so I want it to rotate about the z-axis, because that's our vertical axis. So I'll say our W, rigid rotation, I'll come in here. Okay, right turn would be a negative. And so we're going to say, okay, negative 0.5653. 5653. Okay, so now that this is good to go, we have to change the rigid fixed. Now we want it to rotate in the Z rotation, but not an X rotation. All right, so now it's ready to go. We can hit run. However, this model will not be very physiological because it is constrained to only Z rotation. When we do right and left rotation, our um, our spine actually twists out of plane, which doesn't really happen in flexion and extension, but it does in right and left axial rotation. So the best way I've come up with to counteract that is we run this like how it just set up, okay, constrained, and then when we run it, we actually can collect the torque value and then rerun as a torque model using that new torque. And so what we're going to do is we're going to apply a new torque using our best guess as the torque that it outputs in order to reach this angle. And so then we compare, okay, we applied this torque, and now what is the angle we reached? If it's within 1 degree of this value, which I just multiplied by 57.2958, right? So if it's within 1 degree of this value, then we're good and we can move on. If it's not within 1 degree of this value, then we might have to increase the torque or decrease the torque. And that will take a few tries, but that's the best way I've come up with to do it so far. So with that, we've talked about all the different boundary conditions. We've talked about how to take a torque model and make it an applied rotation model in flexion extension, do the same in right and left axial rotation, and then take that right left axial rotation model and switch it up for a torque model again, using that torque as our best guess, and then iteratively making new guesses until we're within 1 degree of this angle. So I hope that all makes sense. Thank you so much. Have a great day.